Welcome to Learning to Engineer. In this video, we are going to see another interesting concept. Why is the average power in a capacitor 0? We saw a similar concept in the previous video. Do check that out before coming here. Okay. So, why is the average power in a capacitor 0? First, we'll understand what a capacitor is and then we'll answer this question. Okay? A capacitor is a charge storage device. It stores the current in the form of charges. The EMF that's developed across the ends of a capacitor, which is E, is directly proportional to the charges that it stores. We all know that current is the rate of change of charges. I is equal to the differential of the charges with respect to time. So, what is charge? Charge is equal to the integral of time, the integral of current with respect to time. Okay. So, this EMF is proportional to the integral of current. Right. So, in order to remove this proportionality constant, we are introducing a constant called capacitance. 1 by C into the integral of I dt. Okay. This current should be of alternating in nature in order for this capacitor to store charges. Okay. So, if a DC current is passed, this capacitor will block DC. Okay. So, what is the instantaneous current? I is equal to Im sin omega t. So, if we quickly substitute, we will get this as 1 by C into the integral of Im sin omega t d omega t. So, this is equal to 1 divided by C. Let me take the constant term outside the integration. So, integrating sin omega t, we will get minus cos omega t divided by omega, which is equal to 1 divided by omega c. Okay, I will make it as Im by omega c into minus cos omega t. So, we will write this minus cos theta as sin 90 minus theta. Okay. So, this is nothing but sin 90 minus omega t. Okay. This instantaneous EMF is this. We will denote this 1 by C, 1 by omega c term as capacitive reactance for our convenience. Let this be Xc or capacitive reactance. So, this instantaneous EMF is equal to Im multiplied by Xc into sin 90 degree minus omega t. So, what do we infer? The instantaneous current is sin omega t and this is sin 90 minus omega t. So, this EMF is lagging the current. If this is the current, the EMF will be late by 90 degrees. Okay. So, this is how the waveform of the capacitor would look like. Okay. This is the EMF and this is the current. The EMF will lag by 90 degrees. Okay. So, why are we discussing all this? Because power is voltage into current. What is average power? The power that's delivered in a period of time. Okay. Since this current is alternating in nature, we don't have a definite term called power. Either it is average power or RMS power. Okay. So, what is the average power? The average power will be 1 divided by the time period of the waveform into the integral from 0 to the time period instantaneous EMF multiplied by the current with respect to time. Okay. We will use this equation using this instantaneous EMF and this instantaneous current. The average power is equal to 1 divided by 2 pi into the integral from 0 till 2 pi Im by Xc Sine 90 minus omega t, Im into sine omega t, differential of omega t. So again we will simplify this by making this as the maximum EMF Em and this omega t to be theta. Okay, so what is the average power? It is 1 divided by 2 pi from the limit 0 to 2 pi Em sine 90 minus omega t. So sine 90 minus theta is minus cos theta. Okay, so this is minus cos theta into Im sin theta d theta, right? So we will club all the constant terms outside. This is equal to minus Em Im by 2 pi from the limit 0 to 2 pi sin 2 theta. I am clubbing cos theta and sin theta as sin 2 theta because sin 2 theta is equal to 2 sin theta into cos theta. So we have only cos theta and sin theta here. So we are bringing the term 2 to the other side. So this is sin 2 theta divided by 2 d theta. So again this term goes to 0. So therefore the average power in a pure capacitor is 0. Thanks for watching. For more videos on similar content, subscribe to Learning to Engineer. And if you have any doubts, you can write to learningtoengineer@gmail.com or you can simply type that down in the comment section. Thank you.